In long-range industrial drone operations beyond the visual line of sight, relying on a single radio frequency link is a critical point of failure. Modern autonomous platforms operating in 26 utilize a hybrid network architecture. They combine the ultra-low latency of ground-based 5G cellular networks with the global coverage of low-Earth orbit satellite constellations like Starlink. The topology is clear. Under normal flight conditions, the drone's onboard computer routes primary telemetry and high-definition video streams through local cellular towers directly to a cloud-based ground control station server. This architecture allows an operator located thousands of kilometers away to command the asset with a latency of less than 50 milliseconds. But out in the physical world, networks are dynamic, volatile, and unpredictable. When a drone travels through industrial corridors, it eventually encounters the biggest threat to wireless automation: network congestion. What happens when a drone flying at 80 kilometers per hour transitions from one cellular sector to another? This process is called a network handover. In a perfect environment, the onboard modem disconnects from the distant tower and attaches to the closer one seamlessly. But if the destination cellular tower is congested, heavily loaded with local data traffic, or experiencing high packet drop rates, the handover stalls. The connection enters a state of high packet latency. For the flight controller running ArduPilot or PX4, this is catastrophic. The telemetry packets, structured in the standard MAVLink protocol, stop arriving at the designated frequency. If the internal safety timers on the drone count down to 0 without receiving a valid heartbeat packet from the ground control station, the system triggers a global failsafe mechanism. The drone aborts its industrial mission, cuts off its payloads, and initiates an emergency return-to-home routine. For commercial operators, these false positive failsafes mean lost revenue, broken flight schedules, and unnecessary wear on the airframe. The problem isn't that the drone lost connection entirely. The satellite backup link was fully operational. The failure occurred because the pilotny controller did not know how to switch interfaces without panicking. To solve this network bottleneck, aerospace engineers do not rely on the drone's primary operating system to handle network priority. Instead, they implement sub-millisecond multipath routing on an onboard companion computer, connected directly to the flight controller via high-speed serial links. The companion computer runs a continuous telemetry routing daemon, such as MAVLink router. The cloud-based ground control station sends duplicate heartbeat packets simultaneously over both the 5G cellular network and the low Earth orbit satellite link. To prevent the flight controller from triggering an emergency routine during a cellular drop, the MAVLink failsafe parameters must be tuned precisely. First, the parameter FS GCS TIMEOUT is extended from the standard 2 seconds to 5 seconds. This gives the network routing layers enough buffer room to handle intense cellular jitter. Second, the telemetry link routing is configured with different priority metrics inside the Linux operating system of the companion computer. Cellular data is marked with a low metric value, making it the primary path due to its low latency. The moment the cellular link quality drops below a critical threshold, the routing daemon executes an instantaneous hot swap. It routes the active MAVLink stream exclusively through the satellite interface port, labeled as Telemetry 1 or Telemetry 2 on the hardware. Because the flight controller continues to receive identical heartbeat packets from the exact same system identity, it experiences zero configuration lag. The system registers 0 heartbeat losses, avoids triggering a failsafe crash, and continues its autonomous mission smoothly, completely immune to the structural limitations of terrestrial networks. Maintaining absolute operational control in a highly contested or unpredictable radio frequency environment is not a matter of luck. It is a challenge of strict system architecture and disciplined software parameter calibration. By understanding the data link layers and hardening your routing protocols, you ensure that your assets remain mission-capable regardless of ground infrastructure volatility. Thank you for watching this engineering breakdown on BlackBox UAV. If you analyze flight logs, build autonomous software stacks, or deploy tactical systems beyond the visual line of sight, make sure to subscribe to the channel and leave your technical feedback in the comments section below. Stay analytical, verify your telemetry parameters, and we will see you inside the next BlackBox session.